We're moving on to this Supplement A chapter, which is about solving systems of equations. In our first section, we're going to be talking about solving linear systems by graphing. Now, you should remember this topic from your Algebra 2 course last year. Largely, this chapter is a rehashing of things that we've already done in our Algebra 2 class, so things should look pretty familiar. We're going to start by defining what we mean by a system of two linear equations. Okay, when we say a system, it means that these two equations have to be taken simultaneously. When we say that it's linear, it means that the variables, the x and y, the exponent has to be 1, and the only operations going on are addition, subtraction, and multiplication. So a two-variable linear system looks something like this here, where A, B, C, D, E, F are just like real number values. So we say that a solution to a linear system is an ordered pair like an xy that satisfies both equations. So for example, let's say that we have the system 4x plus y equals 8 and 2x minus 3y equals 18. And let's say then the solution for this system is 3, negative 4. To verify that this is a solution, I should be able to plug in 3 for x and negative 4 for y. And both equations should be satisfied. So when I do it for equation 1, I get 12 minus 4, which is indeed 8. And when I do it for equation 2, I get 6 plus 12, which is indeed 18. So for sure, 3, negative 4 is a solution, as it satisfies both equations in our system. Everybody okay with that idea? Good. So the question then remains, how do we find these solutions? So one way we can do that, if we think about each of these being linear equations, that means that I could also represent them graphically with a line. And if that point satisfies both equations, or if our solution satisfies both equations, that means that solution has to be a point on both lines, which means that, okay, the places where the two lines intersect would represent our solutions. So let's say that we wanted to do that. So let's just take this same system here. And say now we wanted to solve this by graphing. So the first thing I'm going to do is rewrite my equations so that they're in slope-intercept form. So the first equation, I'm going to subtract 4x from both sides to get the y by itself. And in the second equation, we would subtract 2x from both sides and then divide by -3. And that would be my second equation. Now, to graph the equation for a line, I'm just going to need 2 points on that line, right? Any 2 points will do. So maybe I pick 0. When I plug 0 into the equation, I get, for x, I get 8. For y, and then maybe I pick 2. When I plug 2 into the equation, I get 0 for y. Do the same thing over here. I plug 0 in, I get -6 for y. And then maybe I plug in 6 for x, and that gives me -2 for y. So now that I have 2 points on each line, and you could always generate more than 2 points if you wanted to. Let's go ahead and graph these. Let's see, 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So I'm going to just graph the first equation in blue and the second one in green. So I have 0, 8, and then 2, 0. And then my other one, I'm 0, -6, and then 6, -2. So this is my solution, which appears to be x equals 3 and y equals -4. What's the drawback of doing this, though? Well, neatness definitely counts, right? If you're a little bit off on your drawing, it makes it really hard to get the correct answer, right? Additionally, let's say I 3, -4. What if I was looking for 2.9, -4? Would it be very likely that I could draw a graph accurate enough to where I could tell the difference between 2.9 and 3? Not really. So doing this by hand is not really optimal. What we'd rather do is do this electronically with the calculator. So to do this with our calculator, we'll go to the y equals menu. We're going to plug in the equation y equals -4x plus 8. And then the second equation, 2/3 x minus 6. Now, for an algebraic thing like that's purely algebraic, that's not part of a story problem, and the numbers, the coefficients are relatively small here, I would probably just graph this on my standard window from -10 to +10 for both x and y. So the easiest way to reset your window back to that is to do the Z standard from the zoom menu. So I'm just going to press Z standard. So there's the graph of my two equations. Looks pretty much like I drew below. And to find the intersection of these now, I'm going to press second, and then the trace button, and select the intersect command. And as long as all you're graphing is two lines, all these questions it's going to ask you don't really matter. So I'm just going to press enter 3 times, and it spits out 3, -4 as my solution. You guys all kind of remember doing this last year? Again, we've done that before, so it should be relatively familiar process. Now, the question becomes, is there always just one solution? Right? We've seen that surely if I have two straight lines, they can intersect and give us one solution. Is that the only possibility, though? Well, if I have two straight lines, what else could happen? You could have a situation like this, where the two lines never cross. What would that imply? If there's no intersections, we'd say there are no solution. Very good. And there's one other thing that can happen. Does anybody remember what that one other thing could be? This is the other thing that could happen. Is they actually are the same line, in which case every point on the line is a solution. We say this is infinitely many solutions. I usually abbreviate that as IMS because that's a lot of letters. And no solution I usually abbreviate as NS. Again, just saving myself some writing. Because mathematicians, ooh, we love abbreviations. Okay. So let's take a look at some more examples here for solving. So 4x minus 3y is equal to 8. And then 8x minus 6y is equal to 16. So just like before, I'm going to start by putting these in slope-intercept form. So started by subtracting the 4x over and then divide by the -3. Same idea here. So subtract the 8x over, and then divide by the -6. It's like, okay, well, there's my two equations. So I guess I'll just go and type this into my calculator. And we'll go ahead and hit graph. And when I look at this, it appears there's only one line. So there's two possibilities going on here. One possibility is that these two lines are really representing, are both there. They're just in the same location. The other possibility is the other line is just off the calculator screen somewhere, and it's there, but I just can't see it right now. So the easiest way to check that is to see if I pick a point on the first line, if it gives me the same point on the second line, right? So if I pick x equals 0, I get the y coordinate -8/3. And in the second equation, if I picked x equals 0, I get the y equals -16/6. But -8/3 and -16/6 are the same thing. So this is really just two overlapping lines is what we're looking at. Alternatively, what's even easier than that is if you press second and the graph function, it gives you the table of points, and you can see the points for both equations. The equation y1 and the equation y2 are exactly the same y coordinates for a given x. So we're pretty positive this is an infinitely many solution situation. Now, did I have to actually graph this to notice that? No. If I had gone ahead and reduced the fractions in my second equation, I would have noticed that it's the exact same equation, which would have told me there are infinitely many solutions. So if I had made that observation there, I wouldn't have even needed to graph. Everybody okay with that? But really, for me, I could have told that this was infinitely many solutions without even having to rearrange things. So if I look at the coefficients, I notice that the coefficients in one equation are just 2 times the coefficients in the other equation. That right there is enough for me to tell it's infinitely many solutions without actually having to do any rearranging. Drawing any graphs, I could just compare the two equations. Now, it's unlikely if you're like trying to solve stuff by graph and you'd think to do that right away, which is why I show it to you last. Because I wouldn't expect you to be like, okay, each one of these I'm going to start by checking, But if you notice that, you're done, which is a decent thing to kind of look at in the beginning. But if you don't do it, it's fine. When you rearrange, you'll get the same two equations. Or if you miss that, when you look on your calculator at the graph, you'll just get one line. So there's lots of places where you can see that this was infinitely many solutions. Let's do another. So here we have 2x plus y equals 4 and 8x plus 4y equals 4. So again, we'll start by rearranging. So I'll subtract 2x from both sides. And then the second one, we subtract 8x from both sides and then divide by 4. And maybe we just go straight ahead to graph this. So when I look at these two, what do we see? I see parallel lines, right? Which tells me what? No solution. Now, did I have to go all the way to the graph to see that? Well, no, because I remember that if lines have the same slope and different y-intercepts, that would be enough to tell me that these two lines are parallel, which would imply no solution. So if I just looked at the two y-intercept equations, I could have figured out that this was no solution without having to draw any graphs. Or if I went back to the beginning, to my original equation, and compared the coefficients, I would notice that the x's and y's are the same, but the other one is different. So if I look at one half of the equation, the x and y half, one equation is 4 times the other. But if I look at the equal side, the solution half, that's not the case. That right there would be enough to tell me that there's no solution to this. Any of those interpretations would be fine, whether you analyzed the initial equation, whether you looked at it in slope-intercept form and noticed you had same slopes but different y-intercepts, or whether you drew the graphs and noticed that they were parallel. Any of those are valid reasons to say that there's no solution. Everybody's okay with that? Just a question of like when you kind of noticed it, right? Whether it was right away or did you wait all the way to the end till you drew the picture to notice? So is this as bad as it gets? Almost. So I'd say the worst case scenario for most of us would be a situation where we have like a story problem. Okay, so let's look at an example there. Okay. So here's the situation. You ride a bus from town center to your street. There's two payment plans. Plan A is to buy a monthly bus pass and pay $1 per ride. And then plan B is to just pay $2.50 per ride. A monthly pass costs $30. How many rides will after how many rides will the total cost of the two plans be the same? So the first thing that I would do when I have a story problem like this is I would try to figure out what are my variable or variables, and what are they representing. So typically the easiest way to figure that out is to look at the actual question part. So if I look at that last sentence where the question mark is, it says after how many rides will the total costs be the same? So how many unknowns are in that question? Gabby? Okay, good. Two unknowns. We have the number of rides and the total cost. So let's use R to represent the number of rides and T to represent the total costs of a plan. Everybody okay with that? We're good with how we figure that out and what piece of the story problem kind of gives us that information? Okay. So since this is in the systems of two equations chapter, it's a fair bet that I'm going to be writing two equations here. Those two equations are going to be representing what? Well, if I read the story problem I have, Landon? Yeah, so it's plan A and plan B, right? We're going to have one equation for plan A that represents plan A and one equation for plan B. Everybody feel okay with that? That should feel pretty obvious given that they talk about two different things in here. All right, so let's look at plan A then. Let's start by writing that equation. So it says plan A is to buy a monthly pass and pay $1 per ride. So since we're talking about paying for things, whether a monthly pass or the cost of a ride, those are going to make up my total costs, right? Okay. So it says we have to buy a monthly pass, which is how much? $30. And then pay $1 per ride. So when we have that word "and" in there, what kind of mathematical operation is that representing? Adding, right? So the monthly pass. And then what is $1 per ride? How am I going to write that? 1R, right? So again, per typically is going to mean like a multiplication. Okay? Now let's write the equation for plan B. Plan B says we're going to pay $2.50 per ride. So what do I write here for the total cost for plan B? Yeah. I'm going to drop the 0 at the end of the 250 because, like, we don't care. Alex? Sure. Okay. So let's go ahead and type these two equations in then. I'm going to use X instead of R, though. Everybody's okay with me doing that, I hope, right? It's clearly obvious the calculator needs to use X's and Y's instead of R's and T's. Okay? But I'm not going to hit graph right now because I'm going to actually change my window around. Because in this case, this is a real-world problem with real-world context to it. So our X is representing the number of rides. Can the number of rides ever be a negative number? No. So I'm going to make my X minimum instead of negative 10. I'm going to make it 0. And we're talking about the number of rides in a month. So I don't know what that upper bound would be, but 30 seems like a decent number since there's 30 days in a month. Maybe ride the bus once a day or something. I don't know. Everybody feel okay with that as a reasonable upper bound? I can always go back and change that, but that to me feels okay. The scale I'm not going to worry about. The Y is representing the total cost. Again, can the total cost in this case be negative? No, that would kind of imply they're paying you not to ride the bus or something, which the bus is not going to do that. And then my total cost here. So if I ride under Plan A, if I do that 30 times, I'd pay $60. And under Plan B, if I rode that 30 times, that would be $75. So I think 75 seems like a good upper bound for the Y's. Does everybody feel okay there? So just to match whatever my upper bound is for the X's, but in all reality, it doesn't matter a whole lot as long as you can see the intersection. So if I hit graph now, here's my line for Plan A. There's my line for Plan B. The intersection is the place that I care about, right? That's when the two costs will be the same. So if I hit second and then trace, I pick the intersect command, enter, enter, enter. That gives me the point 20, 50. So I would answer then after 20 rides, the total costs are equal, or something to that effect. Everybody cool with what we did there? Again, the solving part was really, really easy. By far, the most difficult piece of that was writing your own system, right? But again, like, you start by figuring out, okay, what are your variables representing? And then working your two equations out from the other stuff that's given. But you definitely want to start by figuring out what your variables are. Okay? Next up, we're going to be talking about graphing systems of linear inequalities. So again, start with a little definition. Here, there's no real limit to the number of inequalities in our system. We could have 2 or 3 or 10. It doesn't really matter. But the key thing here is that we're making sure that these inequalities are linear. So again, I'm looking at the variables, making sure their exponents are all 1, and that the only operations going on are that the variables are either adding or subtracting or multiplying to real numbers. Does that feel okay to you guys? Okay. So before we start talking about graphing a system of linear inequalities, let's just talk about how we graph like an inequality in two variables like this. So the first step is to pretend it's an equation and find 2 points on that line. After we've done that, we would plot our 2 points and then draw our line. We'd use a solid line if it's an or equal to inequality, and we'd use a dashed line if it's a strict inequality. And then lastly, we're going to shade above the line if it's a greater than or equal to, and shade below the line if it's less than or equal to. And I guess maybe step 0 is we'd want to write this in slope-intercept form. Should probably say that. Zach. Sure. One thing we might want to say here on that last step, number 3 as well. When we say shade above, what if the line is vertical? If it's vertical, above is really meaning to the right. And if the line is vertical, below would mean to the left. Which I hope makes sense. On a vertical line, the big stuff is on the right and the small stuff is on the left. Right? Correct? Hopefully that makes sense. So let's just bulldoze here through a quick example. So the first thing I would do is to put this in slope-intercept form. So subtract 4x from both sides, and then divide both sides by 2. Remember, when we're dealing with inequalities, let's just make that a 6 or something. I don't want to deal with the stupid fractions. That if you multiply or divide by a negative number, if you multiply or divide both sides of your inequality by a negative number, that inequality symbol has to flip directions. You guys remember that? So if you're doing your rearranging, you have to be careful about that. So that's like my step 0. Step 1, I'm just going to pretend that this is an equation. So I pick 0 and I get 3. Maybe I'll pick 2 and get -1. And now it's time to graph. 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. So I'm going to plot 0, 3, and then 2, -1. Because it's a strict greater than inequality, I'm going to draw it with a dashed line. And then since it's a greater than, I'm going to be shading above the line. So you just pick any point on the line and then you're doing above. So there's my step 3, is to do my shading. Now, how many points represent a solution to this inequality? The answer is infinitely many. So for example, even the point here, like 3, 3, that's not on the line, satisfies our inequality that we had here of 4x plus 2y is greater than 6. Since 4 times 3 plus 2 times 3 gives me 12 plus 6, which is definitely greater than 6. So when we talk about the a solution to a system of inequalities, it's every xy that satisfies all the inequalities. So the solution to a system of inequalities is always going to be either kind of an infinitely many solution situation or a no solution. There can't be a case where it's just like equals 1. Without making it really stupid. I'm trying to think. There probably is a way to make it one solution, but like you need to really bend over backwards to get that. I need 4 inequalities that are all kind of overlapping in a weird way. Well, you won't see it. So let's look at an example of what of solving one of these things and what that really kind of looks like, okay? So let's say we have this system of 3 inequalities. So first thing I'm going to do is to rewrite these so that we're in slope-intercept form. Notice in this first inequality, when I divide by -1, I had to change the direction of the inequality symbol. Actually, I want that to be that then. Everybody feel okay here? All right. So we're going to then pretend these are equations and find 2 points that would lie on the line. And that should be pretty easy, but remember the x equals -2 piece. When I have an equation like that, what do the x coordinates have to be? Have to be -2, right? The equation is x equals -2. The only value for x that satisfies that is -2. What do the y values have to be then? Is there a y in the equation? No. What does that mean that y's can be? Anything you want them to be. So maybe 0 and 1. All right, let's see here. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And then we'll do blue and green and I guess maybe red. Okay. So 0, -5, and then 2, -1. And this one was a strict less than. So we're going to use a dashed line. And we're going to be shading below. I'm going to just draw the down arrow, and I'm not going to do any shading yet. The next one I have 0, 3, and then 2, -1. And this one is also a strict greater than. So I'm going to be drawing it with a dashed line. And then here we're going to be shading above. And then my last one is the vertical one. So I have -2, 0 and -1 or -2, 1. And that's a strict greater than or equal to. So that's going to be a vertical line that's solid. And since it's greater than, we're shading to the right. So the place where these three overlap is going to be this section in here. right? That's below the blue line, above the green line, and to the right of the red line. Notice that the red line didn't really matter there because Mr. Gulick picked a bad example. Even if that red line wasn't in there, we'd have the same answer. Oops-a-daisy. But you get the idea, right? So the solution to a system of inequalities is the overlap of their shaded regions. Now, when you draw these, I prefer that you draw just the overlapped region like I've done here. Although it would also be acceptable if you did something where it's really clear, like maybe we'll make the blue ones going this way and the green ones going this way, so it's easy to see where the overlap is. But try to be very careful about what you're drawing to make sure that for the reader, that being me, that it's super clear where the overlap is. Ben? Sure. So easy to see that, like, in a region like this, there's always going to be infinitely many points, right? I also mentioned that you could have no solution here. What would that look like? Well, say you had two parallel lines. The one on top you shaded above, but the one on bottom you shaded below. There's no overlap to the shaded regions. This would be a no solution situation. That's what a no solution would look like, is you have two parallel lines that you're just shading opposite directions of. So there is no overlap. Now, if the two lines intersect anywhere, there has to be some overlap, right? But that's what we would mean by no solution. Any questions on what we've done here so far? I feel like this is a good place to stop. At this point, you guys have enough to do 1 through 8 from the problem set. We got, I don't know, 20 minutes, 15, 20 minutes or so. I would get started. You could probably grind through, the first couple at least. Get something out of your way so you have less to do later.